All right, 5.2, conservation of energy. I'm going to skip over a lot of those questions. The one thing I want to talk about is the pole vaulter before we get going. The pole vaulter's height is going to be measured to the center of mass. So remember, your center of mass is going to be somewhere around your belly button. So as the pole vaulter is going up and they're bending their body over that pole, as you see in your notes, the height that they go is their center of mass. If their center of mass is even just a couple of inches above that pole, then there's a strong likelihood that they're going to successfully clear the bar. All right, on to the test your understanding. A student in gym class wants to measure the speed that he can dash straight forward. The student has a friend who wants to help, but the friend only has a meter stick. No stopwatch. There's a rope for climbing suspended from the ceiling. Explain how the student can use the meter stick and the rope and conservation of energy equation to calculate his dash speed. Okay, so if we've got this kid and he's standing here, that's connected, and he starts running this way. We have a rope over here hanging from the ceiling. This kid can run over here, grab the rope, and then start swinging. And as he swings, he is going to have this motion where it goes like this. So what can this other guy with the meter stick do? Stand over here, hold the meter stick up to see what is this height. What is this change in height? So we'd have to have the bottom of the meter stick level with the bottom of the rope, and then we'd have to mark where they went as in terms of height. Could also do this with a camera, slow motion activated, and you can see. But I guess if you have a camera on your phone, then you probably have a stopwatch too. So we just have to deal with the constraints that we're given. In this situation, there is no phone. All right, so in words, I would write the kid runs and grabs onto the rope. And then the second person is going to measure the height the kid swings, the change in the height that the student causes. So it's basically turning it into a pendulum here. And then we can use our conservation of energy. When he's running, he's got kinetic energy, and when he's way up here, he's got gravitational potential energy. So Ki is going to equal to UGF. And this is 1/2 mv squared equals mgyf. Initial velocity multiplied by 2 on each side. Solving for the initial velocity would tell us how fast he is running. It's going to be 2gy. Mass goes away. Multiply 2 on each side and take the square root because it's v squared. Okay, so we have a block of mass m connected to a spring of constant k. The block starts with a speed v at a height y. Listen, we're getting to a point, whenever you see the word height or height is implied, or a change in height especially is implied, go right to your conservation of energy. The equation is so easy to build. The energies in the beginning have to equal the energies in the end. What kind of energies do I have? I feel like you guys are really good at identifying the types of energies. So put it into an equation form. So the initial height, wherever that was, is going to be right here, and then the final height is going to be right here. Okay, so it goes this distance down the ramp. So let's get to this equation. TMEI equals TMEF. As a reminder to add up all of your energies. So in the beginning, because we're starting off with some height here, that's why I wanted to make note of that, we're going to add in our gravitational potential energy at that point. So gravitational potential energy in the beginning. What else do we have? The spring is already being compressed. It's connected to us, or not compressed, extended, sorry. So we have spring potential energy. What else? It's moving in the beginning, so it has kinetic energy in the beginning. What about in the end? In the end, we still have a height, so we still have UG. Do we have kinetic energy? Yes. But we don't have that full amount of kinetic energy because there's friction involved, frictional force involved. So we've got to deal with that somehow, some way. Is there still spring potential energy? There sure is. So we'll have spring potential energy. And now let's deal with that friction. The friction is going to be the dissipated energy, force times displacement. In this case, our frictional force times the displacement x. Why did I say x? Because it tells me x. Now, we're going to go through and you can... So what are we... Oh, we're just writing an equation. So I would go one step further than this. I would put in all of the variables. 1/2 kx squared plus 1/2 mv squared. And that is v naught squared equals mgyf plus 1/2 kx squared. That's my spring potential energy. Plus 1/2 mv squared, final velocity squared, plus the dissipated energy, or work done by the dissipated energy, force of friction, plus x. I can't cancel out my masses because mass is not available in all terms, right? Normally that's what we would do. Say, okay, mass goes away. But in this case, because there's a spring involved, we can't cancel out masses. So that's it. That's our answer.